the ideal transformer and how this ideal transformer, phasor diagrams and all those things we have seen. Now we'll be seeing a practical transformer. A practical transformer, which is nothing but the transformer which you will be seeing in general basis. That is, whatever you are having, whatever the transformers we are seeing in a general basis are called as the practical transformers. These practical transformers differ from the ideal transformers in many aspects, basically. So the practical transformer has iron losses, windage resistances, and magnetic leakage, giving rise to leakage reactances. So these are the different parameters that are distinguishing between the ideal transformer as well as the practical transformer. So let us see each of them in particular and understand why these are present and how these can be eliminated. So first thing is iron losses. Since the iron core is subjected to alternating flux, there occurs an eddy current and hysteresis loss in it. These two losses together are known as the iron losses or core losses. The iron losses depend upon the supply frequency, maximum flux density in the core, volume of the core, etc. It may be noted that the magnitude of iron losses is quite small in the practical transformers. So why does this iron losses occur? Means these occurs due to the eddy current and hysteresis losses, and then these two losses are together called as the iron losses or the core losses. The iron losses will be depending upon the frequency at which this total what do you say uh, transformer is being operated. Okay, so and then these are quite small in the practical transformer. Next are the winding resistances. Since the winding consists of copper conductors, it immediately follows both primary and secondary will have winding resistance, right? The primary resistance is called as the R1 and the secondary resistance R2 act in series with the respective windings as shown in the figure. So here you can see R1 and R2 are two resistances which are shown as the lumped parameters, whereas those are actually a distributed parameter and we cannot see it practically. But because of the presence of this resistance, those are represented as the lumped parameters of R1 and R2 in this figure. When current flows through the windings, there will be a power loss as well as a loss in the voltage due to the IR drop. This will affect the power factor and E1 will be less than V1 while V2 will be less than E2. So the generated EMFs, from the generated EMFs, you will have a small voltage loss, IR loss, that is R is the resistance and I is the current through the resistance. So IR drop will be there due to because of this there will be a voltage drop and the total generated EMF will not be translated to the terminal EMF. Okay. And the next thing and the main part is the leakage resistances. Both primary and secondary currents produce flux. We know this, right? The flux phi links both the windings is called as the useful flux and is called as a mutual flux. Okay, which links both the windings. That is, if primary and secondary windings are there and there is a change in the primary winding, that will be linked to the secondary winding, that is called as a mutual flux. However, primary current would set up some flux phi which would not link the secondary winding. Similarly, the secondary current would produce some flux phi that would not link the primary winding. Here you can see. So there will be a normal flux between these two windings, which is called as the phi, which is nothing but the mutual flux. Okay, this is the mutual flux. But there will be some flux produced by each of them separately. That is, phi 1 is the flux which is not associated with the secondary winding, and phi 2 is the flux produced by the secondary winding which is not associated with the primary winding. So this flux is called as the leakage flux, whereas this whatever the mutual flux is called as that is called as the mutual flux or linkage flux, which is linking both the windings. Okay, that's what the flux such as phi1 and phi2, which links only one winding, is called as the leakage flux. The leakage flux paths are mainly through the air. The effect of these leakage fluxes would be same as though inductive reactances were connected in series with each of the winding of the transformer that had no leakage flux as shown in the figure 7.4. Here, so this leakage fluxes are nothing but are similar to reactances. So we are representing the leakage flux, whatever the leakage flux is there, that in the form of these reactances x1 and x2, where x1 is the leakage flux of primary winding and x2 is the leakage flux of the secondary winding. In other words, the effect of the primary leakage flux is to introduce an inductive reactance X1 in series with the primary winding as shown in the figure. Similarly, the secondary leakage flux phi2 introduces an inductive reactance H2 in series with the secondary winding. There will be no power loss due to the leakage resistance. However, the presence of the leakage resistance in the windings changes the power factor, as well as there will be a voltage loss due to Ix drop. So these X1 and X2 are the represented leakage reactances, which will not have any power losses, but there will be a voltage drop due to the reactances. Ix drop will be there because of the reactances, and because of the presence of this inductive element, reactive element, what happens is the phasor diagram which you are going to see will be a little different than the normal, what do you say, uh, ideal transformer. Okay, it will be different from the ideal transformer. So there will be change in the power factor of the machine because of the presence of these leakage reactances. Note, although leakage flux in a transformer is quite small, about 5% of the main flux compared to the mutual flux, yet it cannot be ignored. It is because leakage flux paths are through air of high reluctance and hence require considerable EMF. Um, EMF. So because of the this path is being in the air, that is, air has very high reluctance when compared to the other ferromagnetic materials, right? So the core is of ferromagnetic material, that's why it will not have any reluctances. Reluctance is nothing but the resistance for the magnetic flux, that is equivalent to the resistance in the electrical, whatever the electrical parameters are there where we are using resistance. In the magnetic circuits, you call it as the reluctance. That is nothing but the virtue of the material to oppose the flow of the flux. So if you take a ferromagnetic material, this ferromagnetic materials will have a low reluctance, that is they'll allow the flux to pass through them easily, whereas the air doesn't allow the flux to pass through it easily, because of which in order to make the flux to pass through air, we'll need to have a large amount of EMF setup. Okay, so because of which we will be having losses. Okay, so the loss of the voltage, not anything else, you will be having a loss of EMF. Okay. Next is a practical transformer on no loads. Till now we have seen the construction of the practical transformer and what are the different parts that need to be taken care and all those things. Now we are going to see a practical transformer on no load. Okay, so consider the practical transformer on no load, that is the secondary is an open circuit, as shown in this figure. Here you can see on the right left hand side, bottom left hand side, you can see the figure where he is showing us the practical transformer with no load. The primary draws a small current I naught to supply the iron losses and a very small amount of copper losses in the primary. So in case of the ideal transformer, it is drawing small amount of current which will set up the magnet, which is called as the magnetizing current, and which will set up the magnetic flux. Whereas in case of the in case of the practical transformer, you will be having some losses, right? You need to feed those losses. In order to feed those losses, you will be drawing a small amount of current from the supply I naught. which is called as the I naught. Hence, the primary no load current I naught is not 90 degrees behind the applied voltage but lags it by an angle less than 90 degrees as shown in the phasor diagram. Because this is not an ideal condition, and here the what do you say, primary winding is having some resistance, because of which it cannot act as a pure inductor. So you will not have exactly 90 degrees between the current and the applied voltage. Okay, so you will have some angle which is less than 90 degrees, and you will have the current setup. Here you can see, in this diagram you can see here, I naught is lagging by some angle phi naught. Okay, I naught is lagging by angle phi naught. Okay, no load input power is W naught is equals to V1 into I naught cos phi naught. So why are we saying I naught cos phi naught? Means you have to take the what do you say, component, right? You have to take the component. Here IW is the component. IW is nothing but I naught into cos phi naught. So the total no load power that we are giving to the machine is W naught is equals to V1 into I naught cos phi naught. So this is the phasor diagram. You need to, will further develop this phasor diagram. Let us see. As seen in the phasor diagram, the no load primary current I naught can be resolved into two rectangular components. That is, the component IW in phase with the applied voltage. This is known as active or working or iron loss component, and supplies the iron loss, and a very small primary copper loss. So the basic thing is, you are dividing this phasor I naught into X component and Y component, and the Y component is nothing but the component which is in series with the voltage, applied voltage. So that parameter will give us the how much of loss that is being fed to the transformer, and that voltage, sorry, and that component is called as the working or iron loss component or active component of the total current. Next, the component Im lagging behind the V1 by 90 degrees and is known as the magnetizing component. Here we have another component, right? If you are taking X component and Y component, the Y component is the active component or the iron loss component, which is feeding the iron losses of the machine, whereas Im is the X component, which is at exactly 90 degrees away from the applied voltage, and this component is called as the magnetizing component, which will produce the mutual flux in the core. Okay, so Im is equals to I naught into sine phi naught. And again, clearly I naught is the phasor sum of Im and Iw. This we know, right? And again, at no load, the power factor will be cos phi phi naught is equals to Iw by I naught. You know what is power factor, right? It is nothing but the what do you say? Mm, the angle, cos of the angle between two parameters, right? So here in this case, V1 and I, the cos of the angle between the voltage and current is called as the power factor. In this case, V1 and I naught are the voltage and currents respectively. Now the if you need to know the power factor, you need to take the cos of the angle between them. Here the angle between them is phi naught. So cos phi naught will is equals to cos means adjacent side by hypotenuse, right? Here the adjacent side will be IW and the hypotenuse will be I naught. So cos pi naught is equals to IW by I naught. It is emphasized here that no load primary copper loss is very small and may be neglected. It will be very small, that's what he's saying. Therefore, the no load primary input power is practically equal to the iron losses in the transformer. So whatever the power we are giving is nothing but the iron losses in the transformer. So that is how we are taking it, because the resistance will be very small and the copper loss which we are going to get, that is I naught square into R1, will be very small. Okay, so it can be neglected. So no load input power W naught is nothing but the iron loss. Note, at no load there is no current in the secondary, so V2 is equals to E2. on the primary side, the drops in R1 and X1 are there due to I naught are very less because of the smallness of I naught. Hence, we can say that at no load V1 is equals to E1. Even though on the primary side we have this R1 and X1, because I naught is very small, you will get this I naught, you will get this R1 and X1 drop will be very less. So we can say that V1 is equals to even on the primary side as well. Next is ideal transformer on load. Till now we have seen the ideal transformer on no load and how the flux is being set up and all those things. Now we will be seeing the ideal transformer on load. How the ideal transformer will act if there is a load present. Let us connect a load ZL across the secondary of the ideal transformer as shown in the figure. Here you can see, here in this figure you can see that there is a load ZL that is being connected to the transformer, secondary of the transformer. The secondary EMF E2 will cause a current I2 to flow through the load, right? Because there is a closed path, you will have a voltage of E2 in the secondary, and then you have a closed path, so that there will be a current setup I2 in the closed path. Now, the angle at which I2 leads or lags V2 or E2 depends upon the resistance and reactance of the load. Okay, so first of all, I2 is given by E2 by ZL or V2 by ZL, whatever you want to take. Now, this angle at which this I2 will lead or lag the voltage will depend upon the resistance and the reactance of the load. Okay, in the present case, we have considered inductive load. So, the current I2 lags behind V2 by phi 2. So, here he is taking an inductive load. So, if it is an inductive load, then the current lags behind the voltage by some angle. Because it is not a pure inductive load, you will be having some angle phi 2, which is like behind the voltage. The secondary current I2 sets up an EMF, sets up an MMF, that is magnetomotive force, and then into I2, which produces a flux in the opposite direction to phi, originally set up by the primary by the magnetizing current. This will change the flux in the core from its original value. However, the flux in the core should not change from its original value. In order to fulfill this condition, the primary must develop an MMF which exactly counterbalances the secondary MMF N2 I2. Hence, a primary current I1 must follow such that N1 I1 is equals to N2 I2, or I1 is equals to N2 by N1 into I2, that is K into I2. Basically, what happens here is, now because there is a current that is being set up in the secondary of the transformer, because of this new current which is being set up, that is I2, there will be a flux N2 I2 will be set up in the transformer. This N2 I2, whatever the MMF that is being produced, will be opposite to whatever the mutual flux which we had before, that is the mutual flux which was set up by the primary current I naught, that will be changed, that the value of that will be opposed by this N2 I2, but that value should not change. For the transformer to work properly, the core flux, whatever the core flux is there, that should not be changed. So in order to counterbalance whatever the extra flux that is being produced by the secondary of the transformer, what happens is the primary will draw some current from the source such that that value is equal to the MMF produced by the extra current which is being drawn by the primary will be equal and opposite to the amount of MMF that is being set up by the secondary, that is N1 I1 is equals to N2 I2. Okay, it will be exactly equal and opposite in direction, such that those two fluxes will nullify, and the primary flux, that is the mutual flux which has been set up in the starting of the machine itself, will be not disturbed. So how much of current should this I1 draw in order to make sure that that value of flux is not changed? Means, here you can see I1 is equals to N1 I1 should be equal to N2 I2, right? And again I1 is equals to N2 by N1 into I2. You know what is I2, and you know N2 by N1. N2 and N1 and N2 are a constant values, so you will not have any change in them. So I1 value should be equal to K into I2 such that whatever the what do you say, whatever the mmf that is being produced by the secondary is being counterbalanced. Thus, when a transformer is loaded and carries a secondary current I2, then a current I1 is equals to K into I1, okay, K into I2 must flow in the primary to maintain the MMF balance. In other words, the primary must draw enough current to neutralize the demagnetizing effect of the secondary current so that the mutual flux phi remains constant. Thus, as the secondary current increases, the primary current increases in unison and keeps the mutual flux phi constant. The power out input therefore automatically increases with the power output. For example, if K is equals to 2 and I2 is equals to 2 amperes, then the primary will draw a current I1 is equals to K into I2, that is 4 amperes. If the secondary current is increased to 4 amperes, then the primary current will increase to 8 amperes. So whatever you do, there should be a constant mutual flux. In order to maintain the constant mutual flux, the primary will be drawing extra current, which will set up a flux N1 I1, which is equal to N2 I2, and then counterbalances it. Here in this diagram, in this phasor diagram, you can see that currents. Okay, basically there will be a flux set up. First thing is you will be having a secondary current I2 which is set up the phi 2 degrees from the E2, and then in order to counterbalance this you will be having another current I1. Yeah, here you can see I2 is there. Here you can see I2 is there. In order to counterbalance I2, there will be a setup I1 which is exactly opposite and equal to the I2 value. Okay. Now here he is going to give us a brief description of the phasor diagram. So figure 7.72 shows the phasor diagram of an ideal transformer on no load. On load. Note that in drawing the phasor diagrams, the value of K has been assumed to be unity so that the primary phasors are equal to the secondary phasors. The secondary current lags behind V2 by E2 by phi 2. It causes a primary current I1 which is in anti-phase with the secondary current. So I1 phi 1 is equals to phi 2, that is cos phi 1 is equals to cos phi 2. This the power factor on primary side is equal to the power factor on the secondary side. Here phi 1 and phi 2 will be equal and opposite. So phi 1 and phi 2 values I1 and I2 will be equal and opposite. So phi 1 and phi 2 will be similar values. So the power factor of the primary side will be equal to the power factor on the secondary side. Since there are no losses in an ideal transformer, input primary power is equals to the secondary output power, that is V1 I1 cos phi 1 is equals to V2 I2 cos phi 2. So because of there are no losses, right? Okay. So we have some problems based upon all these parameters which we have seen till now. Let's see those problems. Okay. Just a second, I'll just open this window. Yeah. Here you can see. So these are the let me zoom in. Yeah. So first thing is it is an example problem. He's giving us a 2000 by 200 volts 20 kilowatt ampere transformer has 66 turns on the secondary. Calculate the primary turns, primary and secondary full load currents, neglect the losses. So here you can see 2000 by 200 volts. He's giving us both the voltages, that is the highest voltage as well as the lowest voltage at the same point. Okay, and he is giving us 20 kilowatt amperes. That is the total power, which is a constant value, right? So there will be, this is how the ratings will be given. That is, the highest rating will give you whatever the high voltage rate winding is there, for that whatever the highest voltage is there, that will be given, and then the secondary or this smaller voltage will be given. So this is how the total what do you say, representation will be 2000 by 20 200 volts. So and then he is giving us the what do you say, total power of the transformer, which is always given in volt amperes. Volt amperes, nothing but V into I, volt amperes. Okay, so here is giving us 20 kilovolt amperes is the power of the transformer, and he's saying that there are 66 turns in the secondary, and we need to calculate the primary turns as well as the primary and secondary full load currents. Here is asking us to neglect the losses. So we are drawing a diagram which is representing whatever the what do you say, data that is being given. Here you can see whatever the data that is being given. So primary is there, secondary is there, and you have the voltages V1, 2000 volts, and then again 200 volts. He is giving us the voltages and all those things, and then and then we have this E1 E2, and we know that N2 is equals to 66 turns, but you can see that k value is given in the problem itself, right? K value is nothing but k is equals to V2 by V1. You know what is V2 and you know what is V1, right? V2 is 200 volts and V1 is 2000 volts, so the k value is equals to 1 by 10. And once you know k value is equals to 1 by 10, you can easily calculate the number of turns, right? N2 by N1 is equals to k. So just by plugging in N2 value in this equation, you can say that N1 is equals to 660 turns. And he's asking us to calculate the full load currents, right? So in order to calculate the full load currents, you need to know the power of the total power of the machine. So you know what is total power of the machine, which is 20 kilowatt amperes. So kilovolt amperes. So V1 I1 is equals to V2 I2 is equals to 20 into 10 power 3. Now I2 is equals to V by, sorry, power by voltage, which is power is 20 into 10 power 3, whereas V2 is 200. So if you do that, you get the I2 value as 100 amperes, which is nothing but the full load current of the secondary. In the similar manner, you know what is k value, right? You know, after knowing the k value, you can directly find out the I1 value as I1 is equals to k into I2, which is nothing but 100 by 10 amperes as I1. Alternatively, you can just do the same thing which we have done for the uh, I2, that is taking the total power and dividing it with the voltage of the primary. That is 20 into 10 power 3 divided by 2000 will give you 10 amperes. So that is the one problem. Let's go for the next problem. He is giving us an ideal 25 kilowatt ampere, sorry, kilovolt ampere transformer has 500 turns on the primary side and 40 turns on the secondary side. The primary is connected to 300 volts 50 hertz supply. Sorry, 3000 volts 50 hertz supply. Calculate primary and secondary currents on full load, secondary EMF, and maximum core flux. So these are the things we need to calculate. So the first thing is same thing again. We'll find out the transformation ratio K is equals to N2 by N1, which will give us 4 by 50. Okay, so and we need, first thing is first I1 and I2 values we need to find out. So I1 value can be found out by directly writing the volt amperes by voltage of the primary. We know what is the volt amperes, that is 25 kilovolt amperes is being given as the power of the machine. So we write that, and then we have the voltage of the primary, that is 3000 volts. So if you write the 3000 volts, you get 8.33 amperes as the total primary current, full load primary current. After knowing the full load primary current, you can calculate the full load secondary current by just plugging in this transformation ratio. So I2 is equals to I1 by K. So I2 by I1 is equals to, sorry, I1 by I2 is equals to K, right? So, sorry. Yeah, I1 by I2 is equals to K. And now, if you know K value, you can just put on that value into this equation and you can get the I2 value as 104.2 amperes. Similarly, he's asking us to find out the EMF produced. So E2 by E1 is equals to K. E2 is equals to K into E1. You know what is K value and what is E1 value. So you can directly find out the E2 value as 240 volts. Again, we need to calculate the EMF, sorry, the flux produced in the core. He is asking us the flux produced in the core. So we know this equation, right? E1 is equals to EMF equation of the transformer, 4.44 F into N1 5M. So in this we know, except 5M we know everything, right? E1 is equals to 3000 volts, and again phi is 50 hertz, and then N1 is 500 turns. So if you know everything, just calculate the 5M value. Here you can get the 5M value as 27 milliwebers. So that is the maximum. He's asking us that, right? The maximum core flux. Phi m is nothing but the maximum core flux, which is given as 27 milliwebers. Okay, the next problem is, here he is giving us a single phase, a 220 volts by 250 volts 50 hertz transformer has a net core area. He's giving us areas here, okay? Net core area of 36 centimeter square, 36 centimeter square, and a maximum flux density of 6 Weber per meter square. Calculate the number of turns of primary and secondary. So he's giving us flux density as well as net core area. So you can find out the total flux, that is phi m. Phi m is given by Bm into A. Bm is the flux density, maximum flux density into core area. Core area is given as 36 centimeter square. So 36 into 10 power minus 4. So you can get phi m as 0.0216 Weber per Weber, not Weber per meter square, Weber. So you know E1 is equals to 4.44 into F into N1 into phi m. You know phi m, you know F, you know E1. So if you can just take N1 as your what do you say, um, subject, you can say that N1 is equals to E1 by 4.44 into F into 5M. So here you can calculate the N1 directly as 459. Similarly, you can calculate N2. Once you know 5M, you can calculate either of the values, right? So N2 is equals to 52 in this case. So this is how we can calculate this problem. Next problem is similar to what we have seen in the last problem, same thing. Here he is even not giving us the direct length of the material. So let us see. A single phase 50 hertz transformer has a square core of 20 centimeters. The permissible maximum flux density in the core is 1 Weber per meter square. Calculate the number of turns of the limb on the high and low voltage sides of 3000 by 220 volt ratio. To allow for insulation stampings, assume that the net iron length to be 0.9 into gross iron length. So here is giving us that the square is 20 centimeters square. Centimeters square. It is, the core is 20 centimeters. And it is a square having a side of 20 centimeters. But because we need to calculate for the insulation, he is saying that the net length of the side should be taken as 90% of whatever the length is there. That is 0.9 into 20, which gives us 18 centimeters. So now we need to find out the cross sectional area. Here you need to remember that this is only for the length, the breadth is not being changed. So if the breadth is not being changed, then the total cross sectional area will be become a rectangle which is 18 into 20. If you just do that, you'll get the cross sectional area as 360 centimeter square. Okay, and again same thing how we have calculated in the previous problem. Phi m should be calculated as bm into a, where bm is given as 1 weber per meter square, and again you know what is the cross sectional area, so you can calculate phi m. In the similar manner, even is equals to 4.44 into f into n1 phi m. This is a standard formula, so here you can just write that formula, and then you can calculate the values of n1 and n2. Okay, now let's see another problem. Here till now what we have seen, whatever the four problems we have seen are the problems based upon the transformation ratio. Next we are going to see the problems based upon the currents and this transformers. A transformer takes a current of 0.6 amperes and absorbs 64 watts when primary is connected to its normal supply of 200 volts 50 hertz. The secondary being open circuit, find the magnetizing and iron loss current. So is giving us an ideal transformer, right? No, it's not an ideal transformer. It is a transformer which is on no load. There is no load on the transformer because the secondary is an open circuit. He is asking us to find out the IM and IW values. So first thing is no load primary power W naught is equals to V1 into I naught cos phi naught. We know this, right? Iron loss component is given by IW is equals to I naught cos phi naught, where which is nothing but W naught by V1. W naught is here is given us as 64 watts. So 64 divided by V1 is 200 volts. So 64 by 200 will give you 0.32 amperes. This is for the iron loss component IW. Next, we need to find out the no load current. So, in order to find out the no load current, the equation is I naught is equals to root of Im square plus Iw square. But we know this value of the no load current as 0.6 amperes. So, we need to calculate the magnetizing current, which is nothing but the Im, which is nothing but square root of I naught square minus IW square. We know I naught value, we know IW value. Just plug in those two values and you will get IM value as 0.507 amperes. Okay, so the next problem here we're going to see is on a similar basis. Here also a 230 volts to 2300 volts transformer takes no load current of 5 amperes at 0.25 power power factor lagging. Find the core losses and the magnetizing current. Here he is giving us cos phi naught directly. Instead of saying what is phi naught, he is giving us cos phi naught directly as 0.25. So we need to take the iron losses. Sorry, for the first thing is we need to find out the core loss. Core loss is nothing but W naught is equals to V1 I naught cos phi naught, right? So V1 is 230 volts and I naught is given as 5 amperes and phi naught cos phi naught is given as 0.25. So if you do that, you get the W naught as 287.5 watts. In the similar manner, we need to calculate the iron loss current, which is nothing but IW is equals to I naught into cos phi naught. You can just directly multiply I naught into cos phi naught and you'll get 1.25 amperes. And then whatever we have done in the previous problem, Im is equals to root of I naught square minus IW square, which gives us the Im value as 4.84 amperes. So the next problem is a 230 by 2300 volts transformer takes a no load current of 6.5 amperes and absorbs 187 watts. If the resistance is 0.06 ohms, find the core loss, no load per factor, active component of the current and magnetizing current. So we need to find out the core loss, that is W naught and again no load power factor, and then active component of the uh, active component of the current and the magnetizing current. So first thing is no load loss W naught is equals to 187 watts. So primary copper loss due to no load current. Here you need to understand that he has given us a primary resistance of 0.06 ohms. So if you are having a resistance of 0.06 ohms, then there will be a primary copper loss, and that primary copper loss needs to be accounted for. So it is take it if you calculate the primary copper loss, you will get 2.5 watts. So from so the total iron losses is nothing but the core loss minus whatever the total net loss minus the iron copper loss, right? So if you remove that, you will get the copper loss as iron loss as 184.5 watts. Now we need to calculate the no load power factor, which is given by W naught. We know that W naught is equals to V1 I naught cos phi naught. So here you need to find out cos phi naught. So you know what is V1 I naught and W naught. If you just plug in all those things, you will get no load power factor as 0.125 lag. Now we need to calculate the active component, that is IW is equals to W naught by V1, from which we can calculate the W naught IW as 0.81 amperes. And then we need to calculate the magnetizing current, similar formula, Im is equals to root of I naught square minus IW square. You know what is I naught and you know what is IW, and then you can calculate the Im as 6.4 amperes. So let's stop here for today's class. Let me take the attendance.